Hey guys, what's up? Hopefully things are going on well for you today. I'm making some progress. Dr. Ming and I have started grading the exams. We're getting close. A few are done, but we have to finish up the rest. So as soon as they're done, we'll share it back with you, and you can see your answers and grades and all that stuff. So also we'll put everything online, grades on Moodle and stuff like that. So it's going well. Just got to keep plugging away, chugging away, getting those grades done. So that's our goal. But yeah, so went pretty well overall. I think a lot of people did fairly well on most of it. But yeah, we'll let you know whenever we get them done. So hopefully you watched the 4.2 video or 4.3 video last time. We introduced the idea of linear equations with constant coefficients, like second order, third order, fourth order, not just first order. So we already know how to do first order linear equations. That's integrating factor. Now we're going to look at second, third, fourth, fifth, whatever order you want to talk about. So the linear equations that we talked about last time were second order. So just a recap from last time. So recap, second order, linear homogeneous equations. So we have something like a y double prime plus by prime plus cy equals 0. And from there, we got the characteristic equation am squared plus bm plus c equals 0. And this was our characteristic equation. Characteristic equation. Some people call it the auxiliary equation. And there are three things that could happen. So three things. The first thing is m1 not equal to m2. We have distinct real roots, and we finished off with an example. So distinct real roots. We did an example of that last time. What we want to pick up today is m1 equals m2, and it's a repeated real root. So repeated real root. And then number 3, maybe m1, 2 are equal to alpha plus or minus I beta. So we have complex conjugate roots. So complex conjugate roots. We'll talk about 2 and 3 today, and then we'll get into higher order equations after that. So that's where we finished off last time. We did an example of distinct real roots. Today, let's look at what happens if you have a repeated root. So discussion, question, what if y equals e to the mt is a solution of the differential equation a y double prime plus by prime plus cy equals 0, but m is a repeated root. Well, what do we know in this case where it's a repeated root? Last time I told you that this was when b squared minus 4ac equals 0. So the radical, the discriminant under the radical is 0. So if we have a repeated root, that means b squared minus 4ac equals 0. So how do we find a second linearly independent solution? So how do we find a second linearly independent solution? So the answer is reduction of order. So let's look at taking our equation, rewrite it in standard form. So get y double prime plus b over a y prime plus c over a y equals 0. And here's our p of x. So then the reduction of order formula tells us that y2, we'll call it y2, actually p of t, since we're using t. y2 of t will be y1 of t times the integral 1 over y1 of t squared times e to the negative integral p of t dt dt. So we're basically going to derive a second linearly independent solution for repeated root. So this is going to be e to the mt times integral 1 over e to the mt squared e to the negative integral b over a dt dt. But what is m? M is equal to negative b plus or minus square root of 0 over 2a. And that's because the discriminant is 0 for repeated root. So m is equal to negative b over 2a. So this integral, let's get e to the mt integral 1 over e to the 2mt e to the negative m, let's see, negative b over at dt, which will be e to the mt integral, let's see, 2 times m would be negative b over a, so e to the 1 over e to the negative b over a t times e to the negative b over a t dt is just e to the nt integral of 1 dt. So this is going to be t e to the nt, and that's our second linearly independent solution. So for repeated root, y sub h of t is equal to c1 e to the mt plus c2 t e to the nt. So that's our general solution for the homogeneous equation if we have a repeated root. So let's look at an example. All right, let's look at kind of example here. Y double prime minus 10y prime plus 25y equals 0. Find the general solution. So find the general solution, and the way we're going to do that, just go straight to the characteristic equation. Go to m squared minus 10m plus 25 equals 0. So we go straight to the characteristic equation. And that is going to factor as m minus 5 quantity squared equals 0. Which tells us that m equals 5 is a repeated root. So m equals 5 is a repeated root. Which means y1 of t is going to be e to the 5t. And then y2 of t, we know we just multiply by t, so this can be t e to the 5t. It's y2. So then the general solution, yh, it's going to be c1 e to the 5t plus c2 t e to the 5t. That's our general solution. And if we had initial conditions, we would solve for c1 and c2. So then solve for c1, c2 if given initial conditions. Cool, cool. Any questions so far? Any questions so far? Nada. Nothing so far. Good stuff. Pretty easy. This section overall is not super complicated. I think it's going to be pretty straightforward. The rest of the section as well. But let's get into complex roots. So complex conjugate roots. Complex conjugate roots for a y double prime plus by prime plus cy equals 0. So basically, if we have complex conjugate roots, then that means our roots m1 and 2 are equal to something like alpha plus or minus I beta, which means our solution yh would be c1 e to the alpha plus I beta plus c2 e to the alpha minus I beta. And what we can do is use a little algebra to break that up and say that that's like c1 e to the alpha e to the I beta plus C2 e to the alpha e to the negative I beta. We can factor that out as C1, or factor out e to the alpha. This e to the alpha times C1 e to the I beta plus C2 e to the negative I beta. And depending on what C1 and C2 are, this could be either a sine or cosine function. So if you remember Euler's formula, or formulas, they say that sine x, or sine of t, will be equal to e to the I t minus e to the negative I t over 2I, and cosine of t be e to the I t plus e to the negative I t over 2. So depending on how you combine these two, it could be sine or cosine. So this could be sine beta t or cosine beta t. So we will actually say that y1 of t is e to the alpha t cosine beta t, and y2 of t is e to the alpha t sine beta t. It's kind of a hand-waving argument. I'm not going through the full derivation. But these are going to be the two linearly independent solutions to the complex roots. So then y sub h be equal to C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t, if you have complex roots, where m was equal to alpha plus or minus I beta. So this is a very common solution to a differential equation. It happens a lot in the real world. Springs, anything that has any kind of oscillation in it, even dampening, this is going to be your solution, some kind of oscillatory solution, sine and cosine functions. So this is like a real-world application of complex numbers. Complex numbers usually turn into sines and cosines, oscillations. So let's look at some examples. Example, solve y double prime plus y prime plus y equals 0 for the general solution. So find the general solution. So we get m squared plus m plus 1 equals 0. We'll go straight to the characteristic equation. And let's see, that's going to be m 1 and 2 equals negative 1 plus or minus the square root of 1 squared minus 4 times 1 over 2, just using quadratic formula. So that's going to be negative 1/2 plus or minus the square root of negative 3 over 2. So that m1 and 2 are equal to negative 1/2 plus or minus I squared root of 3 over 2. So then the general solution, y sub h, well, we got to identify what alpha is. Alpha is negative 1/2, beta is square root of 3 over 2. So y sub h of t is going to be e to the, or c1 e to the negative 1/2 t cosine square root of 3 over 2 t plus c2 e to the negative 1/2 t sine square root of 3 over 2t. Probably a better way to write that is factor out the e to the negative t over 2 and leave it as c1 cosine square root of 3 over 2t plus c2 sine square root of 3 over 2t. That'll make it easier when we're actually plugging in our initial conditions, but we don't have any for this problem. But if we did, this would make it much easier. So let's look at another example where we maybe do have initial conditions. So we'll say example here. Solve the initial value problem, IVP, and it'll be the differential equation y double prime minus 2y prime plus 2y equals 0. Y of pi equals e to the pi, and y prime of pi equals 0. So solve the initial value problem. Any questions so far? I don't know why, but it feels like super early today for some reason. I know it's the same old 8 o'clock every day, but it seems unusually early. Looks like we're pretty slim on people as well. Only about half the class is here. So, is anybody awake? I know Philip is. He started the day off right. Yeah, definitely. Yeah, good to have you, Caleb. Good to have you. Yeah, I don't know what's up, man. It's just crazy. It's a crazy, I don't know. It's weird. It's a weird morning. Feels like, I don't know. Feels super early. But we'll make it. We'll make it. Any questions so far? I'm so glad we used Discord then. Came in use. So glad we do that. Let's see. Guess we'll plug in or solve the equation, plug in our initial conditions to solve for the constants in this one. So let's go all the way through. It's going to be a wild ride. Hang on. Going to try to spice things up a little bit this morning. Hopefully it's all good. No, yeah. Well, glad you guys made it. Let's see what we can do. Let's solve the equation. Go straight to the characteristic equation, m squared minus 2m plus 2 equals 0. And then get our roots, m1, 2 equals 2 plus or minus square root of negative 2 squared minus 4 times 1 times 2 all over 2. So that's going to be 1 plus or minus square root of negative 4 over 2. So that's 1 plus or minus I. Unless I screwed something up. So it's going to be 4 minus 8, which is negative 4. Yeah. All right, so our roots, m1, 2, are equal to 1 plus or minus I. So alpha is 1, beta is also 1. So our solution y(h) of t is going to equal, I'll write it as e to the t times c1 cosine t plus c2 sine t. So that's our solution, but we want to plug in the initial conditions to solve for c1, c2. So y of pi is supposed to be equal to e to the pi, and that'll be equal to e to the pi times c1 cosine of pi plus c2 sine of pi. And what is sine of pi? Somebody help me out. What is sine of pi? Sine of pi. Anybody? Sine of pi. 0, yes, yes. What is cosine of pi? Oh, on sine of pi, I'm surprised nobody said the number of dislikes on this video. Cosine of pi is a -1. So this is going to be e to the pi times negative c1. So that means what should c1 be? c1 should be -1 to cancel out that negative. So y is going to be e to the t times negative cosine of t plus c2 sine of t. Yeah, so let's take the derivative now. So what's y prime? Y prime, we need a little product rule action. So product rule. Oh no, who disliked? Oh my gosh, I will punch you in the grade. I'm just kidding. That is so wrong. So wrong. Oh man, somebody disliked. Ouch. Product rule is going to be e to the t times negative cosine t plus c2 sine t plus e to the t times derivative of the second, which is going to be sine t plus c2 cosine t. And what is y prime of pi? Y prime of pi is supposed to be 0. It's going to be 0 e to the pi times negative cosine of pi plus c2 sine of pi plus e to the pi times sine of pi plus C2 cosine of pi. Let's see, cosine of pi, that one's equal to -1, so this is -1 plus C2 times 0, and this is 0, and this is -1. So this can reduce to e to the pi times 1 plus e to the pi times negative C2. Is that right? It's supposed to be 0. So I think C2 should just be 1. So C2 equals 1. And then that'll cancel, it becomes 0. So then y of t is going to be e to the t times negative cosine of t plus sine of t. That's our general, or that's our specific, that's our unique solution, because this is an initial value problem. That's going to be our unique solution. So unique solution. So if we graph this, what does this look like? Well, exponential function grows. And we know that a sine and cosine function can be written as a single sine, shifted sine function, so it's going to look like this. So that's what this solution looks like graphically, if you're to graph it. So questions? All right, how do we get C1 as -1? Let's go back up right here. Basically, I have e to the pi right here, and I have e to the pi negative C1 right here. So basically e to the pi equals e to the pi times negative C1. So that would tell me that C1 needs to be -1, because I want e to the pi on both sides. Good question. Do one more example. One more example. Then we'll go to higher order equations. Try not to talk too loudly. Don't want to scare you guys in the morning, early in the morning. We'll call this differential equations ASMR. Example. Find the general solution of the differential equation 2y double prime plus 2y prime plus 5y equals 0, and discuss the behavior as t goes to infinity. Okay, I'm gonna stop talking like that. It sounds ridiculous. All right, so the solution goes straight to the characteristic equation. 2m squared plus 2m plus 5 equals 0. Now our roots m1, 2 going to be given by the quadratic equation, the quadratic formula, sorry. It's going to be -2 plus or minus the square root of b squared, which is 4, minus 4 times 2 times 5, all over 2 times 2. And that reduces to -2 plus or minus square root of -36, all over 4. So m12 going to be -1/2 plus or minus, let's see, that's going to be 9 times 4, which is like, oh, that's just -6. So 6i over 4 is 3i over 2. So alpha is -1/2, beta is 3/2. And so our solution y of t is going to be e to the negative t over 2 times c1 cosine 3 over 2t plus c2 sine 3 over 2t. So this is the general solution of the differential equation. And what is going to happen to this solution as t goes to infinity? So note, as t goes to infinity, e to the negative t over 2 goes to 0. So solution will decay over time. And so graphically, if you were to look at that, basically be the opposite case. So it starts to funnel in where it was oscillating up here. It's a exponentially decaying oscillation. So exponentially decaying oscillations. All right, any questions so far? Any questions? We'll take a second, take a pause, absorb. Hey, Justin. Great to have you today. Hope you're doing well, man. Thanks for joining us. Smash that like button and punch the person in the face who had the dislike. I'm just kidding. Unless that was you, then punch yourself in the face. Just throwing it back to some differential equations today. Yeah, thanks, man. Thanks for joining us. Just another day in the paradise of differential equations. Oh, yes, there we go. Heck yeah. Sweet. Yeah, we're about to get into higher order equations now. Higher order differential equations, higher order linear equations. All right, so let's let's look at some examples of higher order equations. So higher order equations. So example, what if we have something like fourth derivative of y plus or minus 5y triple prime plus 6y double prime equals 0. So if we have some kind of differential equation like this, we go straight to the characteristic equation again. So we go straight to m to the 4 minus 5m plus, or 5m cubed plus 6m squared equals 0. So we go straight to the characteristic equation. Let's see. What can we do with this characteristic equation? We can factor out m squared. So that's m squared times m squared minus 5m plus 6 equals 0. So then, let's see, can we factor the, yeah, we can factor the parentheses. So we get m squared times m, let's see, minus 2m minus 3 equals 0. Let's see, we have m equals 0 is a repeated root. So m equals 0 is repeated. M equals 2, m equals 3. Those are distinct real roots. So what we're going to do to form our general solution is basically follow the same guidelines from a quadratic, but just keep in mind that we have, in this case, 4 things that we need to add together. So y sub h of t is going to equal c1 e to the 0 t plus c2 t times e to the 0 t, because 0 is repeated, plus c3 e to the 2t plus c4, my favorite, e to the 3t. And what we can do is reduce that, because e to the 0 is just 1, so that's c1 plus c2 times t plus c3 e to the 2t plus c4, my favorite, e to the 3t. And that's y of t. That's our general solution. So this is the general homogeneous solution. So you basically just follow the same guidelines from quadratic. If you have distinct roots, then they just get added. If it's repeated, it gets multiplied by t. If it's repeated multiple times, you just keep multiplying by t. So like if it's repeated 3 times, in this case it was repeated, like we had 2 copies. If we had 3 copies, I would multiply by t squared. If I had 4 copies of a root, I would multiply by t cubed, and so on. I have no idea what that means, but it's super funny for some reason. 8 o'clock. So the t on the C2 comes from the repeated. So this is repeated. So I multiply it by a t. So I do it by itself first, and then I multiply by t for m equals 0. Yeah, sweet. So just kind of follow the guidelines from quadratic. And yeah. Let's get that one. This is a good one. Let's see. Actually, I want to come back to that one in a second. Do a different one first. Let's look at this one. Example. Let's say we have fourth derivative plus 2y double prime plus y equals 0. It's a good one. We'll do it, and then we'll do a little bit harder. Do one that's a little bit harder. So what do we always do? Go straight to our characteristic equation, m to the 4 plus 2m squared plus m, plus 1 equals 0. So this is going to be m squared plus 1 quantity squared equals 0, right? That's a quadratic. That's actually a perfect square. So we got a perfect square quadratic. M squared plus 1 quantity squared. So this means m equals plus or minus I is repeated. So we actually have a complex root here. So we actually have a repeated complex root. So we have repeated complex root. So what we are going to do is we're going to say that y sub h of t, see alpha is 0, beta is 1. So this is going to be c1 e to the 0 t cosine t plus c2 e to the 0 sine t plus, and all we do now is multiply by t, so t times c3 cosine t plus c4, my favorite, sine t. And that reduces to c1 cosine plus c2 sine plus c3 t cosine t plus c4, my favorite, t sine t. And that's our y. That's our general solution. So really just multiply by t to eliminate the duplicate. So very similar to how we multiply the exponential by t. Well, if it's a repeated complex root, we multiply by t on the sine and cosine. And we get linearly independent solutions, t cosine t and t sine t. So then all four of these functions are linearly independent, so then we add them all together after we multiply them by a constant. So that would be our general solution for this fourth order equation with a repeated complex root. Let's look at another one, and then we'll do something a little bit harder. Let's see, this one we'll do is y triple prime minus 2y double prime minus 5y prime plus 6y equals 0. Again, we always just jump straight to the characteristic equation, m cubed minus 2m squared minus 5m plus 6 equals 0. Oh man, we have a cubic equation. How do we find the zeros of a cubic equation? So find the zeros. So we need the zeros or roots of this cubic equation. Any thoughts, any guesses, any ideas what to do? We do the rational zeros theorem. So rational zeros theorem. And that's basically where we check all the rational quotients of the constant divided by the leading coefficient. So the zeros, or we could say possible zeros, are plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1. It's like all the factors of the constant term 6 divided by all the factors of the leading coefficient 1. So here we have a 1, here we have a 6. So those are our possible rational zeros. So the numerator is all the factors of the constant, and the denominator is all the factors of the leading coefficient. So I'm just going to do some synthetic division. So we have 1, negative 2, negative 5, 6. I'm going to try 1 first. So what do? Just bring this straight down, get a 1, multiply, put it here, we get a 1, add these, we get negative 1, and then we multiply, stick it here, we get a negative 1, add them, we get negative 6, multiply, stick it here, negative 6, add them, we get 0. So that means m equals 1 is a root, which means that m cubed minus 2m squared minus 5m plus 6 can be factored as m minus 1 times m squared minus m minus 6. And now we can factor that one as m minus 1 times, and let's see, we can do m, I think it's going to be plus 2 minus 3. So we have 3 distinct real roots. So 3 distinct real roots. Which means our solution y of t will be c1 e to the t plus c2 e to the negative 2t plus C3 e to the 3t. So basically m1 equals 1, m2 is negative 2, m3 is 3. Any questions so far? All right, so those are all pretty straightforward. This one is going to be a little bit more involved. So one more example. This example says, it says an nth order linear differential equation with constant coefficients L of y equals 0, so that's our differential equation, has a characteristic equation with the roots m equals 1, 1, 1 plus or minus 2i, 3 plus or minus 2i, 3 plus or minus 2i. What is the order of the differential equation and the general solution? So what is the order and the general solution of our differential equation? So what can we see? We can see that m equals 1 is a root of multiplicity 3. M equals plus or minus 2i. M equals 3 plus or minus 2i is, or we should say, are roots of multiplicity 2. Basically, how many times does it appear as a root? So here we've got 3, 4, 5, 6, 7, 8, 9. So right, we've got 3, here we've got 2, and here we've got 4. So this is total of 9 roots. So we have a total of 9 roots. Implies the differential equation is 9th order. So it's a 9th order differential equation. Now, what is the general solution of this 9th order differential equation? Well, I've got to take care of the multiplicity 3 root m equals 1. So y is going to be c1 e to the t plus c2 t e to the t plus c3 t squared e to the t. And that takes care of m equals 1 repeated multiplicity 3 plus. Then I got to do plus or minus 2i, so that's going to be, let's see, alpha equals 0, beta equals 2. So that's going to be C4, my favorite, cosine 2t plus C5 sine of 2t. And that line takes care of m equals plus or minus 2I. And then the last one is a repeated complex root, and we know to do that we do C6 cosine, actually we have e to the, let's see, alpha is 3 and beta is 2, so I'm just going to factor out the e to the 3t times, and then C6 cosine 2t plus C7 sine 2t plus, and now we multiply by t, so we get C8 t cosine 2t plus C9 sine 2t. And that takes care of the repeated complex root, m equals 3 plus or minus 2I repeated. With multiplicity 2. So then this would be our general solution. Pretty interesting. Good stuff. Any questions? Take a minute. Think about this, decompress, soak it in. Move on to non-homogeneous equations. So that's going to be what we do next. It's non-homogeneous equations. So non-homogeneous equations with constant coefficients. Basically just going to add a step to what we've been doing already in 4.3. This is going to be 4.4. Non-homogeneous equations with constant coefficients. Oh no. Let me go back. Philip said I forgot to add the t. Let me go back. You're so right. Thank you. Perfect. Thank you. Just make a note here. This t just changed. I needed to add that. Thanks, Philip. How would you enter that on WebWork? Very carefully, I guess. Just don't screw it up. I don't think it's that big on WebWork, but maybe not. But just be very careful. I don't know. I'd have to see the exact problem, you know. I don't think it's that crazy though. Yeah, thanks, Sam. Yes, that is correct. Philip caught that, and we just fixed it. Let's see. Okay. We'll just take a break for one more minute. We'll come back, finish up, do some non-homogeneous stuff, and then talk about a more general approach next time for non-homogeneous equations. Just take another minute. All right, so non-homogeneous equations. Section 4.4. Our goal is to solve nth derivative, or a sub n y to the nth derivative plus dot 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 a sub 1 y prime plus a sub 0 y equals g of x, where coefficients are all constants. So coefficients are constants. So the solution from 4.1 is of the form y equals y sub h of t plus y sub p of t. How to get y sub h is 4.3. How do we get y sub p? That's 4.4. So this whole section is really just devoted to obtaining y sub p. So how do we get y sub p of t? So what do? We guess a particular solution. Y sub p is called the particular solution. So we guess the form of y sub p of t and substitute it into the differential equation and solve for the coefficients of yp. So that's going to be our general way that we find the particular solution yp. For example, let's say we have let's say we have y double prime plus 4y prime minus 2y equals 2x squared minus 3x plus 6. So the solution would be always first find y sub h of t, the homogeneous solution. So that's the corresponding homogeneous solution. Corresponding solution to the homogeneous equation. That would be y double prime plus 4y prime minus 2y equals 0. And y sub, let's see, that would be m squared plus 4m minus 2 equals 0. And m12 would be negative 4 plus or minus square root of 16 minus 4 times 1 times negative 2 all over 2, which would be negative 2 plus or minus square root of 16 plus 8 all over 2, which is negative 2 plus or minus, let's see, I can factor to 4. That'll give me 4 plus 1, which is 5. So 4 square root of 5 over 2. So m12 would be negative 2 plus or minus 2 square roots of 5. 6, sorry. Square roots of 6. So then our y sub h of t be equal to c1 e to the negative 2 plus square root of 6 times t plus c2 e to the negative 2 minus square root of 6 times t. So that's our corresponding homogeneous solution. Now, to guess yp, we're going to guess yp of t is of the same form as the right-hand side. So basically ax squared plus bx plus c. We guess it has this form based on the right-hand side. We'll have to modify this in some cases, but we'll talk about that probably on Tuesday next week. So guess yp equals ax squared plus bx plus c, and then take the derivative. Yp prime of t equals 2ax plus b, and then yp double prime will be 2a. And now substitute these three. So substitute these into the left-hand side, call it LHS, left-hand side of the non-homogeneous equation. And if we do that, we'll get, let's see, what were our coefficients? So y double prime plus 4y minus 2. So 2a plus 4 times 2ax plus b minus 2 times ax squared plus bx plus c equals 2x squared minus 3x plus 6. 2x squared minus 3x plus 6. So we've substituted the yp into the differential equation, the non-homogeneous equation, and now what we're going to do is try to solve for a, b, and c. So solve for capital A, B, and C. And it's very similar to what you do whenever you do partial fraction decomposition. Yeah, sorry. Thank you. Missing my 2. Thank you. Yes, sorry about that. Thank you. So now to basically solve for a, b, and c, it's very similar to like partial fraction decomposition. You just have to like group like terms for x squared, x, and constants. So the x squared term is going to be negative 2a x squared plus, and then factor out everything with x. That's going to be 8a minus 2b times x plus 2a plus a 4b minus 2c equals 2x squared minus 3x plus 6. And now compare the coefficients on both sides. So now equate coefficients on both sides. So the negative 2a here goes with the 2 here in front of the x squared, and then the coefficient of x goes with the coefficient of x, and then coefficient, the constant, whoops, constant goes with the constant. So the constant here goes with the constant here. So we get negative 2a is equal to 2. We get 8a minus 2b equals negative 3. And then 2a plus 4b minus 2c equals 6. First equation tells us a is negative 1. Second equation would tell us that negative 8 minus 2b equals negative 3. So b would equal 5 over negative 2. And then substitute both of those into the last equation. We get negative 2 plus 4 times negative 5 over 2 minus 2c equals 6. And that's going to tell us that c is equal to negative 9. So then yp of t is negative x squared minus 5 over 2x minus 9. So our general solution, y of t equals yh plus yp equals c1 e to the negative 2 plus 2 squared to 6t plus c2 e to the negative 2 minus 2 squared to 6t. And then our particular solution is negative x squared minus 5 halves x minus 9. And that is our general solution for this non-homogeneous equation. How do you get the last group? Is it which one? The pink one? So basically take all the constants on the left and set them equal to the constants on the right. Constant is anything that doesn't have an x with it. So just kind of highlight, like the red one goes here, green one here, and the pink one here. Yeah, cool. We call this method the method of undetermined coefficients. So this method is called the method of undetermined coefficients. So method of undetermined coefficients. So we chose the particular solution to be of the same form as the right-hand side of the differential equation. And it was a quadratic over there, so we just picked the most general quadratic we could, Caleb. So that's how we pick our, well, most of the time, that's how we pick our particular solution. So here's a little table for choosing YP. So some notes. Method of undetermined coefficients, we'll call it MUC, only works for polynomials, exponentials, e to the x, and sine or cosine, or products of these. So we can only use this method for polynomials, exponentials, and sine or cosine. we cannot use it for, like, let's say secant or 1 over x or tangent or something crazy, you know, something more complicated. For that, we'll need a variation of parameters. That's the next section. So, so a table for choosing yp based on g of x, based on the form of g of x, or g of t. We could say x, doesn't matter. So let's say g of x is over here. What are we going to pick for yp of x? Well, first of all, if maybe g of x is like 5x plus 4, or maybe something like 3x squared plus 2, well, what we would pick for p would be a linear function, ax plus b, or a quadratic function, ax squared plus bx plus c. So it just mimics the form of the right-hand side of the differential equation for the most part. We're going to talk about it probably next time. We'll talk about what to do in cases where you can't just follow this table directly. And I'll highlight when you know that you can't just use the table directly. Let's say we have something like sine of 4x. Then our particular solution would be a cosine 4x plus b sine 4x. So even though our g of x only has sine, we actually have to include the sine and the cosine in our particular solution, because the derivatives, you know, like sine differentiates to cosine and etc. So you might have to include a cosine in the particular solution. Let's say you had e to the 5x. Then you would guess something like a e to the 5x. Let's say you had a linear, like 9x minus 2 times e to the 2x. Then you would guess a linear function, ax plus b times e to the 2x. Let's say you had something like, I don't know, e to the 3x times cosine 4x. Then your particular guess would be e to the 3x times a cosine 4x plus b sine 4x. Not to be confused with what people trade on the stock market. 4x. Let's see. What else could we have? Maybe like a quadratic times sine. So if you had something like x squared sine 3x, you would guess a quadratic ax squared plus bx plus c times cosine. It's a quadratic times cosine 3x plus a different quadratic, ABC. I don't want to use d, so I'll go to e x squared plus fx plus g times sine 3x. So we have a quadratic times each trig function with different coefficients. And then I'll just write it on the left. You can try to figure out what it would be on the right, but let's say you had something like x times e to the 3x times sine of 2x. You think you could figure out what that would be? So it would be linear times e to the 3x sine 2x plus different linear times e to the 3x cosine 2x. So you try that one out. See if you can figure that one out. the example. And we'll wrap it up after this example. Say we got a y double prime plus 4y equals x cosine x. Guess the form of yp of x. And we should say naively, because we have to take into account something next time. Naively guess the form. So we would just go ahead and guess yp of x is going to be ax plus b cosine x plus cx plus d sine x. We don't want to use d. D is bad because that's like our differential operator, so we'll skip that. We'll go to e. And that's naively what we would guess for the solution, particular solution. Do one more. So we got y double prime minus 9y prime plus 14y equals 3x squared minus 5 sine 2x plus 7x e to the 6x. So what we have here is actually a G1, G2, G3. So G1, G2, G3. So we're going to have YP1. So we're going to guess YP1, YP2, and YP3. So we guess YP1 based on G1 would be ax squared plus bx plus c. YP2 we would guess as can't use ABC e cosine 2x plus f sine 2x. And then YP3 we would guess a linear function. Let's see, EF G, so gx plus h e to the 6x. And then for yp, we would add those together. So yp of x be equal to yp1 of x plus yp2 of x plus yp3 of x. And I'm not going to write it all out, but that's the idea. If you have functions added together, you just add them all together. Yes, Sam, that is correct for the table, the last entry of the table. Good job. All right, sweet. I think we're going to stop there. We have to be careful, though. We have to be careful because this doesn't always work. So we can't always. So just a note of warning. Sometimes we must modify our YP guess from what's in the table based on y sub h of x. And we'll talk about that next time. So we'll start off with one more example next time. We'll go through, find the coefficients, and then we'll talk about, okay, when can you not just use the table directly? When do you have to modify the table guess? So we'll do that next time. But we'll wrap it up here for today. So any questions? If not, you can head out. But I'll hang around for just a second, see if there are any questions. All right, dude. Have a good one. See ya. Have a good weekend. All right, you guys have a good weekend. I'll talk to y'all later. Hit me up on Discord, group me, or whatever if you have any questions. See y'all.